here's the presentation that I'm going to be talking about today on Vector API. So Vector API is here, and we're going to talk about Vector itself. We're going to talk about SIMD. We're going to talk about species. Awesome. If that API has something called species, that's amazing. Lanes and components. We'll talk about masking, lane-wise, cross-lane operations. My material is here. For anyone who knows me, you know that my presentations are, they have demos, and I usually have more than just slides. I actually have code that is runnable. So everything is over here. So if you want to take a picture right now of the QR code, you can go ahead and do so. If you would like me in the picture to pose along with it, that will cost you extra, and we could talk about that after the session. All right. All right. So yeah, everything is there. So let's talk about the Vector API. So this is going to be an API used to express vector computations. And this isn't for anyone who's like old enough to remember. There used to be a collection on the JDK called Vector. That's not what this is. This is something else. And this allows us to do vector instructions on supported CPU architectures. Architectures. So the performance from this is going to be very fast, and that's the thing that we get from this. And this is part of Project Panama. So what we're going to be talking about is single instruction, multiple data, where we get to exploit parallelism, but not necessarily concurrency. So parallelism is actually doing everything in parallel. So if I have, this one computation, a second computation, third computation, do it all in once, right? And concurrency is possibly a parallelism, but maybe not. At some point, you'll have a timeshare situation where you are vying for control. There's context switching within your CPU. But this right here is going to be actually parallelism that we're going to be talking about. Not all machines offer the ability to process SIMD processes, but the good news is for most major architectures, most major laptops, most major server machines that you'll be using, you do have SIMD capabilities within your CPU, okay? Binary operation applied to two vectors with the same number of lanes would, for each lane, apply the equivalent scalar operation on the corresponding two scalar values from each vector. And I'll tell you what that means, because that sounds really nerdy, but I have some images there that will help you along, some animations that I hope will help along with that. And so we'll describe what that fourth bullet point is down in finer grain detail. This is not new. This has been used in supercomputers since the 1960s and 70s. Anybody know what movie this is from? It's an older movie. Anybody? You know, all right. Was this a foundational movie for you, Andres? In a way, yeah. I think for a lot of, I don't know, do you have like Gen X here in India? Like as far as like Gen X, Gen Z, does that apply here as well? Like, yeah. So for Gen Xers like myself, this movie came out in 1992. I think you'll dig it a lot, but it was about this code cracker and this code that was able to crack anything. And it's a really good story. And then right over here, these are two old friends, but one of them ended up getting placed in prison while the other one was able to escape and is on the run. Robert Redford is on the run, and Ben Kingsley over here is he's part of the underground. Anyway, this is a Cray machine, and so this is like really one of the cool parts of this movie. And right before this, he's like pointing up at the speakers because they're listening in on him. And so in order to have like a private conversation, they enter this Cray machine, which is a computer. You walk into a room and it's a computer. That's absolutely amazing. I kind of want to walk into my computer, but that's part of the movie there. If you get a chance, take a look. And it's called Sneakers. Absolutely a great movie. And I think you'll dig it a lot. But anyway, that Cray machine there had SIMD as well. So it's been around for a while. And by the way, these Cray machines, you have more power. I think you have more power in your phone than you may have for some of these Cray machines. So, we are definitely spoiled nowadays. So what modern machinery has this SIMD capability for our CPUs? All x86 processors, you may hear the term AVX. AVX is the instruction set that can do SIMD parallel processing. And so for those Intel or AMD-based chips, that's what you're looking at. For those with Mac, and I see everyone with a Mac machine, particularly if you have a M1 machine, you'll be using a Neon instruction set for that one. Other processors are available, but for the good folks over at Java that provide this for us, and the good folks over at Oracle, they're going to just be focused on the machines that, and the architectures that we mostly use, which is x86 and ARM. So what are the use cases for this? I'm really excited about this because when you do machine learning, what language do you usually use for that, right? And I think we all know that's right, Python. Python's the answer for that. I kind of don't want it to be the answer, to be honest with you. But Java doesn't have things. I think we do now, or at least we're getting extremely close in order to do this processing. How many of you have done machine learning in Python? So you've used pandas, maybe scikit-learn, maybe TensorFlow. And if you take a look at it, you know that behind the scenes, everything is like a C library, right? And that's part of what makes it fast, because Python isn't inherently fast, right? It's a interpreted language, so it's slow. It's like, all of a sudden, how did this get fast? And how did this become, the language for machine learning? And where did that come from? So Java in that regard, I think, was falling behind. So I think for the second bullet point here, this machine learning and AI, that's what I think is going to be a really, nice way to do these kind of computations. Because for anyone who's done any kind of ML programming, you deal with arrays, right? So pandas and what's the NumPy, right? NumPy are based on arrays, and then pandas is the panel data based on those particular arrays. But you're just dealing with arrays. That's what this is. We're just dealing with arrays, but we can do things in parallel. We can do things extremely fast, and that's the kind of thing that we need. The other thing we need, and I'm going to be talking about tomorrow, is the foreign function memory interface, and the ability to use graphics cards. I think is going to be an important thing as well, right? Because a lot of the the new AI stuff absolutely needs to use CUDA libraries in order to gain access to those video cards. So the combination of these two, I think, are going to kick the door open for us. So that way we can get ahead within the Java space in order to do ML. Let me just add here, AI. AI is, or at least the way I perceive it, is ML that's already been packaged and been deployed, right? That is, the neural networks have been deployed, multiple, millions of feature sets that are able to take your request and do something with that. And so, for the AI side, I think Java's doing pretty well. And there's been a lot of talks here on how to integrate with AI and how to prepare things with RAG and MCP as well. So I think we're doing good there, but the machine learning side, not so much, and I think this will be a really good thing. Fast computation of arrays, gaming, physics engines, imaging, audio, cryptography, right? Because cryptography is just arrays of bytes that you're just dealing with there. So we have a lot of use cases. So how do we try to achieve parallel processing in standard Java today? Break up the data into small chunks and perform your calculations. But when you do so just with standard Java, you're using threads. Vector API is not using threads, and that's going to be one of the differences there. In standard Java, it might be performed concurrently, but not really in parallel, right? Because you only have a certain set of processors, and things need to be time shared on those processors in all likelihood. But Vector API is parallel computation, not concurrent, and that you're going to be loading things up. We're going to talk about the lanes and how that works. And then, wham, just like in one CPU clock, we get to run everything and do the calculation based on that. Okay? Uses large amounts of operating units, executing the same operation at the same CPU cycle at the exact same time, right? Load it up, calculate, and then finish with that. This does require the C2 compiler in order to do so. All right, I don't know if this image is going to translate here. Anyone know what the image on the, this is the one, Andres, I don't know if it was funny or not. I was hoping to get some laughs on this, but maybe it doesn't. But the one on the left, anyone know what that is? All right, so in America in the 1980s, there was a band called Van Halen. And in 1984, Van Halen had a hit song called Panama. Nice. And on the right-hand side, this one is from a movie you could watch on YouTube. It's about 30 minutes long. It's silly, but it's called Kung Fury. Anyone watch Kung Fury? Right? Kung Fury is a good movie. Anyway, so I think that's the war on that side. Anyway, he's representing Valhalla. So there are two projects within Java, Valhalla and Panama. So what's going on here is that Vector API is on its 8th incubator, I believe, and it's waiting for Valhalla to be released. So what you're looking at now as far as the Vector API, I think is fairly solid now. I don't know, we could see some surprises when it does finally get released. But it's waiting for things from Project Valhalla, particularly inlining classes so that way you don't have to box and unbox. And so that way we could just deal with primitives. Because when you box, you store things on the heap. So as far as the memory, all object memory gets stored on the heap. So we kind of want to remove that as well. And what they're working on is something called primitive classes that allows us to declare classes, but in the end, they are just going to be in primitives. So that way they get just placed on the stack and not necessarily on the heap. So in order to get that full performance out of everything, that's why the Vector API is not released currently. Okay, cool. So we move on to species. So what is a species? So when we look things up for our SIMD processes, we have to declare what species are we going to use, okay? And so we could say we want to use byte, short, int, long, floats, or doubles. And what you'll need to do is you'll need to know the size of what can be handled, anywhere from 64 bits to 512 bits. But that's going to be based on the processor that you are using, okay? So you can't just arbitrarily say, I want to use by 12, right? It's just always going to be based on the processor and the instruction set on that particular processor that you're using, okay? But that's called a species. So you'll set that up, and we're going to show some code here in a bit. Next are the vectors. Vector computation is consisting of a sequence of operations on those vectors. And these have a fixed sequence, kind of like arrays of scalar values, where they correspond to the number of hardware-defined vector lanes. Wow, I'm really throwing some stuff at you. So we'll see some images here very shortly. So a binary operation applied to two vectors with the same number of lanes would, for each lane, apply the equivalent scalar operation on the corresponding two scalar values from each vector. Anyway, did I write this? No. I got that from the JEP, and that's the way that he described it. So some information for you right now, but then we'll take a look at some image so that way you can see that. Now, when you say you want a vector from a particular species, what's going to happen behind the scenes is that you're going to be dealing with this type here called vector E. And E, of course, is the generic term for the types of elements that you're dealing with that vector. So you'll have a byte vector, a short vector, int vector, Victor vector, okay, sorry about that, long vector, etc. Okay? So this is going to be based on the SIMD machine itself. And so therefore that vector E is going to be mapped to a vector register to do these compilations. Okay? And you'll have the flavors for these. And when I run the debugger on this, you'll get to see this because this will say, hey, I'm using int 128 or I'm using int 512 vector, okay? But all this is abstracted away. And so let's take a look at a visual on here. So I created an animation for all of you. Let's see how this works. So you have some memory areas that you're going to be dealing with here, or registers. And you're going to be loading these up, okay? This is kind of like, I don't know what a good analogy is. Maybe you could help me along with this. But it seems like something that you load up on a machine and seal it, and then you press the button and it just does it, right? I don't know what the good analogy would be for that one, but I am loading these items up. So what's going to happen now? So I'm loading these up with numbers. This is a vector. So 1, 3, 5, and 2. Right over here, this is a vector. 4, 6, 9, and 3. And right over here is going to be my result set, but that 2 is also a vector, okay? These right over here are lanes. So this is going to be one lane of computation. This is going to be another lane of computation, another lane of computation, and another lane of computation. The number of lanes that you can have are going to be based upon the processor that you are using, okay? And that's the way that's going to work. We also call this components. So we have 4 components because we have 4 lanes, okay? And again, we're just loading them up and then doing the computation, okay? So 4 total components, and again, maybe that's all I get because that's the processor that I have and that's the instruction set that I have, which I think on my computer, that's what it is. Now, in one CPU cycle, again, true parallelism here, wham, there it goes. And that computation is going to come up with an answer, and we're going to load that one up onto a vector, okay? And there we go. And so once that one's done, we have our results set, and then we can continue on. And even though I have, in this example, 4 lanes, let's say I'm trying to add 2 arrays, that can go on for, I forgot what the JVM size is for an array, but I think it's like some huge number. So you can have, really large arrays, but the way that's going to be computed is 4, 4, 4, 4, 4, 4, 4. And so therefore I will load up on another set. Okay. Maybe. Yeah, there we go. So I'm going to load up with another set of numbers. That's going to be a part of my array. And you kind of get the idea here. Again, these are going to be the vectors, the up and down, and the side to side are going to be the lanes. Okay. CPU comes around, CPU clock. True parallelism, we're going to do our computation, and then we are set. Okay, nice. Now, SIMD register width, let's say that my processor is allowing 256 bits, right? And so you would just have to know your processor. But again, you could just run a vector API example and know how many bits are going to be supported there. The size for a float is 32 bits. You know what? Now that I'm doing this presentation, I should have made it a kind of a trivia question there, like how many bits that is. But float here is 32 bits, and double would be 64 bits. But let me just state right here, byte short, int long, float double. It could be an int. It could be whatever kind of type that you want. But you know the sizes for all those types, right? Byte is 8, short is 16, int is 32, long is 64. Float is 32, the other one, double. Boolean, I think Boolean's 1. Ooh, that's a good question. I totally forgot about that one. Is it 1? Andres? Yeah, okay. Cute. All right. So float is 32 bits. So the number of lanes that we're going to have, words are parallel processing that we have, is going to be W divided by S, which is the width and the float, which is going to be 256 divided by 32. Or the number of lanes that we're going to have is 8. All right. You with me? Was that okay? I wasn't too nerdy, right, with all the images and everything? All right, cool. Or at least I hope so. I wasn't waiting for a response, but let's go ahead and take a look now at adding a standard vector. I'm going to go ahead and open this one, and we could take a look here at how to set things up. Right over here, we have vector species, and I'm going to use float throughout all this, but just keep in mind you have float vector, int vector, byte vector, whatever kind of size that you want. But I'm going to stick to float on this one. What I'm going to have here, let me just move down over here, and I'm doing things on purpose for these particular examples. And what I'm going to have is I'm going to have two floats here. No, get back over here. I'm going to have this float, and I'm going to have this float right over here. Keep in mind, 10 elements. I'm doing that on purpose. All right, I'm going to have this float over here, and you kind of have to change your brain again to kind of like C style of code. Remember when you learned C probably back in university, you had like one array, another array, but then you had to open up another array to fill the answer into that array. Kind of the same thing is what's going to be happening here. So I'm going to be creating a brand new float where the answers are going to go. All right. So what I'm going to do then is just system out printf, and we're just going to take a look at the length of each one just to validate that. That's going to be 10, of course, or at least should be 10. And then I'm going to do this vector computation here. And all we're going to do is we're going to do an add on each one, okay? At the end of all this, what I'm going to do is I'm going to print the size of the species, which also should give me the length. So the size of the species is a certain size, but that's also going to be the size of the lanes for my processing. And so therefore, the total amount of memory available is this many bits. And so all I'm going to do here is get the float size, which is going to be 32 bits, and I want to multiply it by the species length, okay? And then what I'm going to do here is print out the answer. Now, what's inside of this vector computation? So in order to use the vector API, what we're going to do here is I'm going to call float vector from array, okay? And we're going to load it up first with the species, and here's a signature here. Take a look there. Notice that. That is the species and whatever it is that you want to do with it. And so I'm going to load it up with this array, and I'm going to say start with this particular index. Same over here. I'm going to do this with load vector from array B. Okay, and there it is. And then what I get to do with this is I get to do any kind of operation that I'd like. Everyone with me so far? So I have these vector A, vector B, and I could do an add. I can do a multiply. I could do a blend. I'll show you what blend is. Broadcast. I could do compare. I could do a compress. That's going to be essentially kind of like a filter. Equals. I don't think I've ever used expand. So some of these I need to do some learning on here. But you get to see here, you have a lot of different operations that you can use. Okay. And so this is all going to be operating on that one CPU cycle. This right here is loading up the answer into the C array. Remember, the C array is going to be this one right over here, which is going to be the result. Okay? Not bad, right? We all got it? Because I'm going to give you homework. All of you have to be a part of a project, and you have to ML library for Java. So, and that needs to be done by next week, people. Sorry, I'm giving you a tight deadline on that one. All right, let's go to run that one. Okay. I don't know if this is the one that's going to blow up. No, it isn't. The next one will. But here it is. This warning is just that I am using something that is not officially a part of Java yet. So here's the warning here. Let me go ahead and expand this here. So A is 10, B is 10, C is 10. The size of the species is 4, which means that given the amount of memory of 128 bits, that's what my processor supports. I have 4 species, and therefore I have 4 lanes that I get to deal with. So load them up, 4 calculations, and that's it. Now, something's gone wrong here. What went wrong? It did the addition for 4 of them, but it left the other ones blank, okay? So what I need to do is load, calculate, load, calculate, load, calculate, load, calculate, right? And that's the thing that I need to do. Now, on this next one then, I'm going to attempt to do that, but this is not going to work. So everything else being the same right over here, so all this is the same, 10 elements, and I'm doing that on purpose here. So here's the computation. And this time what I'm doing is I'm doing a for loop in here. Some of you are new programmers and functional programmers, and you're probably like, what's a for loop? But a for loop is just going to iterate on that. So I have index 0, index less than a length, so whatever the size is. And the index here, take a look at this. I'm going to jump by, so my species length is going to be based on 4 because that's the number of lanes that I could have. So I'm going to jump 4, jump 4, jump 4, jump 4, jump 4, jump 4. And each time I'm going to complete a round, load them up into a vector and run it. Should work, Ryan. Let's see. I'm going to go ahead and run this one and watch it magnanimously fail right there. And it says index 8 out of bounds for number 7. Okay? So it blew up right around there. And the first time I was trying to feel my way around the vector API, I'm like, what am I doing wrong? What's going on? And so I was trying to figure out like this. And it just so happens that it's going to blow up. Let's see if I can try to that situation here. So here it is, and I'm going to do should I step into? Yeah, I'll do a on this one. So this one's going to call check image from size. Here, let me try to do a step into here, and I'll step over. Oh, I think that one was fine. From array. Let's see. I guess it wasn't there. Oh, no, that's right. Sorry, I lost myself. It did work the first time around, right? Because it just did the 4. That's okay. All right. I'm back on track, people. Sorry. So the 4 ended up working because that's fine, because I had 4 values. I'm going to do it again and loop back around. So right over here, take a look with me here. 58.71224848106.5, right? So we just completed one lane. So let me cycle back around, and here it is. We'll go through this one, and we have VC, and notice C right over here, maybe kind of small. Let me go ahead and expand on that. So when I do a step over again, this 4 should be filled. And there it is. All right, so here's my new C. So 4 went in, then another 4 went in, but now I'm in this weird situation. I have 4 lanes, but now I have 2 left, right? Because I have 10 elements. So 4 got filled, but I have, I have that 2 remainder there. And that's where the things blow up. So going, and let me step into, let's see if I could do this one. And I think this is where it blows up. And it did. Okay? So at this point here, this is where we get this index out of bounds exception, because it has 4 lanes, but I only have 2 calculations left. I have these 2 remaining. What do we do with that? So it was hoping to calculate all 4, but I only had 2 because, I need something divisible by 4. And that's where it blew up. Anyway, thanks for coming. I'm just kidding. Cliffhanger there. Oh, man, what happened? All right. So that's where we come to in our next part here. Like, how do we do this, right? I can't, put fake numbers in there, right? That's not going to work. So how do we go about to do this because we have multiples of 4, or at least I have multiples of 4 that I have to deal with? So this is where masking comes in, and you'll be dealing with something called a vector mask. And here's a type here called vector mask. Each element in a mask is a Boolean value. And so this is, if any of you have ever done like bit programming before, right? And you do like XORs or whatever, and whatever that evaluation is, you could filter out some bits along the way. Same sort of concept here. Mask selects the lane operation is applied, okay? So it's kind of like a window where each slice is processed in parallel. And I'll give you an image and an animation for that, and then we'll run through the code so that way you get to see how the mask actually works. So again, everything is going to be this vector mask, and it's used in an operation. And so you could use mask for varying things, not only this. You could use it for filtering, and I believe blending and a few other tasks as well. So in learning this, you'll just have to be, knowing about vector mask. And for any kind of particular mask that you want to create is just a static method. So vector mask something, okay? It's mapped to a predicate register, true or falses. On platforms that don't support this, what you'll want to do with the mask is probably go about it just the general non-vector way. And so one of the things you'll have to determine is whether masking is supported with your particular architecture. All right, so animation time, because you're probably like, what were you talking about? And how does a mask work? So let's say these two are loaded up, 12, 8, 5, and 22. Then what I'll have is I'll have the following. Do I want to include all the numbers? And so here, when they said predicate, that's what they mean here, right? Predicate true, 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 for true, or false. So if I want to include these then the answer is going to be 12, 8, 5, and 22 because they're all true. So just keep all those elements. The middle part here is the mask, okay? But we could use it for other items as well. So 12, 8, 5, 22. Let's say in this case here, false, true, okay? That means that under where it says false, we're going to make that one a 0. Wherever it has true, we'll go in and bring the number down. Wherever we have 5, let's say a 5 and false. Since that's false, that's going to come down to 0. And then I'll have like 22 true, and then that will fall through. Okay, and that's what a mask does. Okay. Now, what if we have true, true, and false, false? Well, we know what's going to happen here, right? But I'm building up to the next scenario. So I have true, true, false, false. And so therefore anything that has false, that won't follow through. So one of the things just before I proceed, if I'm planning to do any filtering, I'll use a mask, right? Because if I want to say, these shouldn't be a part of the next element, then I will do this particular mask. So for those that had raised your hands earlier on you doing machine learning, that should look very familiar to you with NumPy, right? Because you had those arrays and you remember how you used to do a filter? Or used to, like it's past tense, we never do that anymore. But same sort of thing, right? That's vector arithmetic using NumPy and pandas. Same concepts here in how you want to do filtering. So keep that in mind. Now, remember I had this scenario. I'm trying to load up 4 so that way I could do a computation on it, but 2 are missing. So whenever we do this, we have true, true, and given the false, false that we have here, we could say, hey, if there's nothing there, just go ahead and make that a 0, even though the size is a little bit off. This will just make a 4 size so that way we can actually run that, okay? And so the way we do this is species, so whatever species you're using, index and range, and you give it the index and you give it the total length there. And if you're off and you're not able to fit that 4, it will go ahead and fix that up for you. And that's what a masking will do. Okay? Cool? All right. So let's do some masking now. And let's take a look at the mask. And here we go. Yeah, let's do vector with a mask. And let's run through this example here. Everything is kind of the same. One thing here is I have masking supported. I think this is a hack, but I think this hack works that you can get the length here. And as long as it's greater than 0, then masking is supported. So pretty neat little hack there. But I think everything else is the same. I'm just going to print out whether masking is supported, but I'm going to add all these. And again, the catch here is it's not perfect. It's not divisible by 4. Here I am doing that. You know what? That's probably a good idea. Thanks, other part of my brain. Sometimes one part of my brain just does things and there's like, why did you do that? Oh, that's why, because it's a good idea, right? So 4, 4, and then 2, right? That's the issue here. And I'm trying to add these together. And since I only have 4 lanes supported by my CPU, 4, 4, and 2, what are we going to do about the 2? So let's go ahead and do that again. And I'm going to do the add. Let me put a breakpoint there. Hope. And yeah, let's go ahead and run this so that way you can kind of see how that mask is going to work. And away we go. So here it is. And what I have here is I have species, index, and range. My index right now is 0. My A length is 10. And you get to see here what A is. But I'm going to jump over that so that way we can see what the mask looks like. And there it is. Float 128, which I should have highlighted for you, but because I have a 128-bit vector, there's where it is. And I have mask T, 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 which is a 2-string representation of this mask, which represents true, 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 and true. Okay? So that means include all of the, all of the 4 on this one. Okay? And notice what I'm going to be doing here is I'm going to be bringing in mask right over here. Oh, by the way, I just learned about this in IntelliJ in working up to their presentation here. And I think if you do a click on here and during a debug mode, it will show you exactly what's happening here. Look at that. So the mask right now is true, 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 true. You know what? I shouldn't have said anything that I just learned it. I should have just pretended that I knew that all along. Boy, that guy knows everything. All right. So there's that one, right? And that's what the mask is. The mask just states here that for this 4 coming in, use all of them as part of this calculation. Okay. So I'll bring that in and bring that in. And notice what it is that I'm adding. I'm adding 4 numbers and 4 numbers together and then loading those up into an array. Beautiful. Okay, so let me do this a second time, which is going to load the next 8 up, and I'm going to add all those as well. And let me do a click here. We get to see what that mask looks like, right? Here it is, true, 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 true. Add them all up. So that's going to be the 8th one, right? Now we're going to cycle back around. Booyah, here we go. Fun stuff here. What's this going to look like? Well, this mask, oh, look at that right there. Remember, all the masks were like math, T, 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 T. But this time now is T, T, and dot, dot, which is just include the first 2. So that way we can make that particular calculation, okay? And that's the idea here. Run it, and let's add those together. No breaks here. And then finally, let's load that up into the array. And when we load that up into the array, one of the things you'll notice there is that it truncated that 0, 0, so now everything's fit. And that's what a mask does, because now it's going to be perfectly fit. But again, you can use a mask for things like filtering. Let's see. A mask. Let's take a look at that one. Let me go ahead and stop that one here. So, what happens if masking is not supported? Well, in this case, you'll use something called loop this. And let's go and see what loop bound is. I'll put a breakpoint right over here, and let's go to run the debugger. So here we go. So here's loop bound. Let me go ahead and run that. And let me go ahead and highlight that. And let's use my newfound thing here. Here it is. So loop bound is just going to determine, how much do I need to go on this. And so that's going to return an 8 on here for that particular loop bound for that one. So I get to do my calculation in here and run it. But, again, if there's no masking support, here's what that is. Now, the thing that you would have to do is you can run the first 4 on vector, second 4 on vector, but I have 10 elements, but the remaining 2, I'm going to have to do this, which is a classic array addition on there. So if you don't have masking, that's the way that you would have to go about it. Okay? Nice. Okay? So, vector operations, and there are different vector operations. The ones we've seen up to this point, particularly because of addition, are called lane-wise operations. And that's just a fancy word for everything stays in its lane. Okay? And so these operations can combine one lane of a vector with a lane of a second vector, and then just, add them together. Okay? And so operations are further classified. You could do unary, binary operations, ternary, test, conversions. Everything like that is going to stay within its lane, right? And so like this one here is just an example of everything staying in its lane. 1 and 4, the vectors are the columns, or at least I made the columns. The row here is going to be the lane. As far as this computation goes, everything again stays in its lane, right? And that's what that lane computation is going to be. But a cross lane is when you do things like shuffling, like sorting, like finding the min, finding the max. If you envision it, you'll see that by doing something like that, even though you may have 2 lanes over here or 1 lane, you're going to end up with a much smaller lane as the result, right? If I determine a min or a max, right, or the top 2 elements out of, multiple vectors, things like that are going to have a shuffle, or not really a shuffle, but I guess kind of a shuffle, where things are going to have to cross onto another lane in order to produce that information. Filter would be such an example. Okay? Well, that's what that is, right? And I probably described it better than these bullet points here. So if I'm determining, for example, a min on this one here, or, the top 2 or anything like that, or maybe I'm just filtering out the bottom 2 in this case here, right? So the shape has changed, and maybe, I'm bringing the 1 or the 3, or if I'm finding the max, I'll just have one number for that. In order to do something like a cross lane, there's another object called vector shuffle that's going to do that particular work for us. Okay, instances, non-concrete subclasses that are going to be using there. Okay, should have the same type, but these are for cross lane. Now let me show you what a cross lane would look like. I got a lot of different ones here. So let's get started with a compare vector and see if this one makes sense for you. So in this case over here, I have, what do I have anyway? I think I still have the same 10 numbers on here. Do I? Yeah. And what I'm going to do is I'm going to do this vector computation here. I'm going to show what, sorry about that. I'm going to show what the species length is. I'm going to use index and range. You know what that is now with the mask. So I'm going to apply that mask to it. And here's VA, which is going to bring in my particular array. And take a look at this one. This one's a compare. So what I want from this is I want a mask, because this would be a filter operation. I want a particular filter where I want all the elements that are greater than 0.50. That's what that is. Greater than 5.0, and I'm going to apply the mask to it because I only want it to run on the elements that it needs to. Then what I'm going to do is I'm going to do this cross-lane operation, which is get me A, which is the vector array, compress, which is a filter, and bring in that compare, or that comparison there. I'll run the debugger so that way you can kind of see what's actually happening. It's going to be an interesting sight. And then what we're going to do here is we're going to take that and put into a particular result with that particular index. And given this index, we're going to have the true count. So this true count is going to return the number of masked lanes that are set. Okay, that's what that does. Okay, so that's what we're going to do. We're going to run it. the first time. So that way, and in fact, you know what? Maybe I'll do this. I'll set the debugger now, so that way you kind of what's going to happen here. So yeah, oh, you know what? Let me run it first. Here we go. So that way we kind of see the run here, right? Here's that result, right? I had 10 elements, but each 4 are being loaded up, and not everything is going to be greater than 0.5. So each round is going to be a little bit less, right? And so you see how that's a cross lane? You know, for every 4, I could end up with 1, 0, or 2, right? And so some of these elements are going to have to, you know, get over to the other side, right? Does that make sense on that cross lane? Okay, cool. Let's discover some of the secrets of. All right, here we go. So I'm going to go ahead and cool bit here. And what I'm going to do is I'm going to go ahead and run that debugger on this now and see what's actually happening. So here I have the particular mask. I'm going to go ahead and run through this. Let's see, I don't think anything's strange here. But let's take a look at compare right over here. And let's do a click on this. Look what that. That is a mask. Cool, right? So this mask is ... t, which means that for the first round, which is this one here, 0.23 is less than 0.5, so I don't want it. 0.45 is less than 0.5, I don't want that. 0.49 is less than that, but 0.9 is, and so that's why that mask is point, or false, t, because I only want that element. So that's the one that's going to be carried. And so if I take that true count, it's the thing that I want to keep along with it. So I'm going to run this n for the next. Am I? Where am I on this? Let me do. Yeah, I'll just keep going here. So here's the next round. VA compare, and I think you kind of get the idea of what's happening with this one here. So if I take a look at this compare now, and take a look at this load here, the second 2 elements are greater than 0.5, right? And you see how that works? But at the end of all this, given this result mask that we are doing here, this is just going to be given the elements that are going to be filtered. So that's the way cross-lane works. Let's take a look at another example here. Let's do a reduce vector. I got 2 reduce vectors, and I don't think I need to do a debug, maybe a little bit, but I don't know. We'll see where we're at here. I think probably this one, you could probably fit this one together for the reduce. This one here is the sum of squares done with SIMD processing. Can you see it? Let me know if you see that here. So I have a float coming in for this one. I'm loading this one into a mask. And what I'm doing for each round is I'm reducing the lanes, and I'm going to add each one, okay? So I'm doing the multiply. This is a square, VA multiplied by VA. So I'm squaring it using the mask, and then I'm going to sum those particular squares. Cool, right? And so I'll take the square root of that to provide that particular answer. But that's also a cross-lane operation as well, because I'm reducing everything, right? Reducing things down to one single answer. So the sum squares on that one is 1.95. That has to be a cross-lane operation. Let's do another one. This one is reduce vector blend. That sounds like a Starbucks coffee. What's your favorite coffee? Oh, reduce vector blend is very tasty. Has a bold flavor to it. All right, so on this one, what we're doing here is we are doing a blend. What's a blend? A blend is a ternary operator, okay? You're familiar with the ternary operator. If some condition is true, then square it. Otherwise, make that one a 0. So here's 0, but we're going to blend that with a squared and a conditional. And if that conditional is true, then this vector is going to be filled in with the square. Okay? That's what blend is. Okay? So in this case, I think it's a very similar operation on here. We're going to get the condition in here, and that will be a vector mask. We're going to square it, and we'll have a condition associated with that. So I think this one is a sum of squares, but only if it meets a certain condition. Okay, and that's what a blend is. You could have a ternary operator along with it. Let's see. And before I get to the big one here, shuffle vector. Here's a shuffle on this one. And the idea for this one is I'm doing a reverse shuffle, which is definitely cross-lane, right? Because I'm totally rearranging everything in the results here. This one's using a there it goes. This one is using a rearrange. Rearranges the lane elements of this vector, selecting lanes under control of a specific shuffle and a mask. This is a cross-lane operation. It has to be, because it rearranges the lane elements of this particular vector. Okay? So that's the idea here, and they have a lot of operators that you can use. And I think once you get over that hump as to like what this is, so here it is. You'll notice the answer here. I had 10, 20, 30, 40, 50, 60, 80. And you'll notice here by 4, this was one batch. So all it did was reverse that one. And then on this batch, it flipped that, right? But that's a cross-lane operation. And that's what that, rearranging, this rearrange here. Okay. So let me leave you with this one. I was like, can I pull this one off? Maybe, maybe not. But I decided to write a machine learning model. Disclosure, I'm not a data scientist, but I do like machine learning, but I would dare call myself a data scientist. But here's my attempt here at linear regressions. For those that haven't done machine learning is training, give it some data, and then what it comes up with are hyperparameters. And I'm using one of the simpler ones called linear regression. And regression means, not that. Regression means regressing to the mean. This machine learning model is a very easy one. So easy, I wrote one using the vector API. But this is the one where like, hey, we can fit you with the nicest shirt that you've ever seen in your life. Just give us your shoe size. And you're like, what? Right? But it's through the proxy of your shoe size that they could determine what the shirt size is and get a pretty good approximation on this. So given this point here, so here are the data points for this, and this will draw a line through it as best of an approximation as possible. So if X is going to be 3.5, then the answer is going to be around 7.1, and that'll be the approximation, okay? So can I do this linear regression using the vector API? Absolutely. So how you tune this ML is what this is going to do is that through training, it's going to figure out what the best intercept and slope is going to be, right? And so that's what we're looking at here. I decided to use the same methods that are, by the way, when we end, make sure you go, woo, so compete with them and make them feel bad. Which is the training, right? So what I want to know from this, and that's what I'm doing here with these species here, is, figure out the best slope and the best intercept, and I'll make this train flag set to true. Predict, I have two different kinds, which is a single element or an array. And in this case here, if I have an array, I want all the results, and I'm going to use the vector API for that, right? I'm not using the regular Java. I'm using the vector API so I can process this machine learning model as best as I can and as fast as I can. Here I am here using that, which is, here's my X, here's my Y. I'm using a linear regression model that I created using the vector API. and I'm doing a fit. This is the training. And again, for anyone who hasn't done ML, this is, you learning calculus or physics or trigonometry or even basic math or whatever, or history exam, is that you have a book and your brain is very much like a machine learning model. You learn things from a chapter and you take the little quiz at the end of the chapter, right? And then maybe you check with the answers in the back of the book. That's you training. You're doing the same thing as machine learning. So when we say fit, that's what that means. So what I'll get here is the slope or intercept. And what this one is if I plug in 3.2, what's going to be the answer from that? Or if I have an answer and I want to do that as a batch, this is what the answer is going to. So here it is, my coup de grace at the end of this, which is, I get to create machine learning models based on this. And again, you're using the vector API for that, so that way things can process very fast, okay? So anyway, I guess that's my thesis, Through this vector API, you could start to do very fast machine learning. And I don't think the vector API is even that difficult, okay? So thank you very much for attending. I hope you got a lot out. Thanks.